Groups. Yeah, how's everyone doing? Awesome. Is that the floor was a different one, the walls had different. I don't know where everybody is, but here we are. Just how people that have. Including everyone online, 12 people present, it's about half the class. And not others. Disappointment is a measure. Because I had those learned. And then. All right. Any questions on anything from the class with regards to games, with regards to anything we've been talking about in class itself? My main announcement is that we are going to be having some kind of, oh my gosh, why can't I think of words right now? Peer evaluation happening in the reasonably near future. So just keep in mind that you are being evaluated, or you will be evaluated by your teammates on both effort and technical contributions. So make sure that you're communicating with the rest of your group mates, that you're contributing to some kind of big picture idea that you've all agreed on for your game. And that your grade will be scaled by that result. So if you are not contributing, you will not slide by easily. But of course, those of you who are here and talking about your game and communicating about your game, it's always the people who aren't here who I'm actually talking to when I say things like this. So yeah, just make sure that you're doing your best. And if you have people in your group who aren't here, then make sure that they are also aware that this is happening. Yeah.
I just have a question about slides, if you're gonna upload them.
Yes.
There.
Yes, I definitely will. Especially ahead of any exam related or game related outcome for the grad students.
The exam week 5, right?
Yeah, not happening anytime soon. Especially since we're only doing 3 hours of this lecture per week, it takes a while to build up enough content to actually have an exam's worth of material. But yeah, last time we talked about using policy evaluation in our grid world example. I'll zoom in on this again so that you can see kind of how this evolves. I just wanted to go back over exactly how this process is working. It is relatively complicated. But maybe I could see a show of thumbs at the moment for how much sense this process makes. Between perfect sense and no idea what this is doing, the perfect sense would basically be you feel like you could implement this. You understand it well enough to write the code. And somewhere in the middle being, I understand it somewhat intuitively, but not enough to where I feel like I could implement it.
Talk about this step specifically, right?
Yeah, these exact steps with regards to coming to this conclusion, given the data and the policy that was the random actions policy. It seems like, for the most part, people are in a pretty good place, which is good. That's better than it's historically been when I've talked about this, so I'll call that a win. So what we're doing, we start out with an initial value here of 0, and as we do this iteration at a time, we are determining what is the average reward that we have when that number of iterations has passed. So after one iteration, we're looking at it. We started at a particular cell. What is the average reward that we have accrued so far after a single step, looking a single step into the future? But we iteratively do this because we're keeping track of the state's values. We're not looking 2 steps into the future. We're looking 1 step into the future from 1 step into the future. So that iteration allows us to say, based on the values of the states that are around, we can update this value based on the expectation of how much reward we're going to get from taking that extra step. And eventually, we converge. We would never reach these values, but we would get closer and closer to these values. You can use calculus or even intuition to figure out what we are converging to, given enough information, enough time steps. But the idea was that this was the correct policy was embedded in this information. If we're looking at this 14, we had decisions between left, down, right, and up. And of those, left made the most sense because it just goes, you greedily select the best reward of those that are around you, given that. So you always want to move right. Given you're at this minus 20, your options are minus 14, minus 20, minus 22, and minus 20. So you want to be going to the minus 14. The minus 22, you're irrelevant. It doesn't matter if you go down or left. From this, we see that we can either go down or left. Here we can go either left or up. Here we go either up or right. Here we always go up. Here we always go, it doesn't matter, up or right. Or haven't we done right there, down there, down there, right there, down there. I think that's complete. Anything I'm missing? I think that's relatively complete. So this is going to become the new policy. Instead of having a generic policy, no matter which state we're in, we're going to randomly select. We can now look at a state by state basis here and figure out what the moves should be. In this state, the only outgoing edge is left. So 100% of the time we should pick left. Where we have this minus 20, where we can get a minus 18 either going left or down, you could decide between 100% of the time doing one of those actions or 50% of the time doing each of those actions. It's mathematically equivalent. The expected value is the same regardless of how much you prioritize the two equivalent actions. But the idea is with this one step, we are done. You can imagine looking at the value of this policy and coming up with the value, how many steps on average would it take for this policy to converge on each of this. And we'll find that when we do that, there's actually no further improvement that we can make to this system. When we go through and find out what values these converge to, it doesn't change the desired policy. We've already derived the optimal policy. Sometimes this takes a few steps. You're going to converge to these values. You're going to make a decision. You're going to change the policy. You'll evaluate that policy, and that will change a few things, but in relatively few iterations, this process will completely converge. And we know that we can't improve it at all from this point because it is mathematically shown at this point. So to give you a sense of what that looks like, this is what we call the policy improvement step. So for a particular state, this is only looking at a particular state. If we had these four options available and we had found over time that that is what these values converge to, then we just change the policy to, instead of having a random selection of values, you greedily select the best value. And you will always do that. So for each state that we go through, we check if there's a better action selection function than the current policy suggests, and we will modify the policy at that state to select the best that it can, given the information that we have. So if greedily selecting an action is better than what the policy currently dictates, then we change it. It's that simple. Just go state by state. As we do this, once we've made a single pass over all the states, we have defined a new policy, since that policy is now defined for any state that you could be in. And then you could improve and look at evaluating that policy. And we would find that when we do see, this is what hopefully I drew in the last slide. When we see that this is the new policy and we apply this new policy, that there is no further improvement to make. That is the optimal policy. So we could check if the value of a policy is equal to the value of the new policy that is selected. That means that no further iterations of this will ever improve the policy. So we can check if the Bellman optimality equation holds. We can look state by state and say, is this the optimal action selection function? And if the answer is always yes, then it will satisfy the Bellman optimality equation, and we're done. We can show mathematically, I'm not going to go through the process, that policy improvement will always return a better policy unless the policy is already optimal. If the policy is already optimal, it'll return the same policy. And you can use that as a termination condition to this. So we can see what the process typically looks like. You just repeat these two steps. Policy evaluation, which was mathematically figuring out the value of being in a state according to the policy. And then policy improvement that says once we've done policy evaluation on every state, we have figured out if there exists a better policy that can fulfill, that improves the values of those states. We can greedily select actions that work better. And we will find that in a very few number of steps, this works. So we evaluate policy 0, improve policy 0 to get policy 1, evaluate policy 1 to get the value of policy 1, improve policy 1, and you get policy 2. And then you evaluate and improve and evaluate and improve until this converges to the optimal policy. Pi star is your optimal policy. And that gives us the best possible values for each of those states. We've optimized the process. What's a problem with this? What is the biggest issue that we could point out with policy iteration? There is something that I have hinted at, but also kind of glossed over with regards to the big thing is, when does this converge? How many iterations of policy evaluation do we need to run before we know what the values that it's converging to are? We go back a slide or two, or 4, k equals infinity. How long is it going to take before we know what those values are that they're converging to? And how long would that take if we are in a system that has more states than grid world? It looks nice when there are only 14 states, 16 if you're including the goals. But that's a lot of work, even for that many states. If we grow the number of states more, that becomes a complicated process to figure out. It may take quite some time to figure out what the limit of this is. It's quite a bit of work. So an improvement to the concept of policy improvement is going to look at that. Let me first give you a little bit of code. Here's pseudocode for policy iteration. And when we say surprisingly few iterations, this is iterations of evaluate and improve, but the evaluate step by itself can take a very long time. So we would like to come up with some procedure that cuts down on that time, because that time is going to dominate the time of this entire process. How long does it take to evaluate a policy? Turns out there is a very easy improvement to this that drastically improves its running time. Anyone want to take a guess? What simple change could we make to policy iteration that makes this whole process take a lot less time? We don't have control over too many variables here.
Start at an already somewhat optimized policy.
Yeah, that's exactly right. Instead of waiting for the evaluation to converge, we could just go through 1 or 2 iterations of policy evaluation. It hasn't converged, but we could immediately try to iterate on that policy and create a new policy. Rather than spending, I'm going to go back yet again to this, and I do apologize for consistently going back and referencing this slide, but you can see how some of the work that is inherent in where to go is already present at time k equals 2. At time k equals 2, if we asked to change this policy, this would always go left. This would always go left. This would always go up. This would always go left or up. This would always go right. This would always go down. This would always go down. Always down. Always right. Always right. It's not an arrow. But that is a significant chunk of the final work that was done by the time we reached k equals infinity. How much time was saved to be able to figure out this mostly complete answer? We went to k equals 2 instead of who knows how long. You can imagine that making this change right here and then trying to evaluate this policy. By the time evaluating this new policy got to k equals 2, we would know more about these middle points and be able to differentiate between those. So we could go through something like probably 4 total policy evaluation loops and have the same answer that takes us 10 or infinity to figure out in this one policy evaluation. So it turns out that the iteration procedure is very useful, and you don't have to wait for that convergence. And in fact, it ends up wasting a lot of time to wait for that convergence. Because the exact values here are not important. What matters is just the relative values to those neighbors, to those next to you. And that starts to become apparent much earlier. If you did need these exact values, that would be a different story. But when you're looking at just relative values, you can use a lot of approximation techniques in ways that make the entire process significantly faster. So typically, algorithmically, always be thinking on those lines. So we call this algorithm value iteration. So instead of waiting for everything to converge, we truncate the policy evaluation. We don't wait until we call for convergence, basically the difference between the maximum difference when we go through that process. We're going to go through every state, and we're going to look at the maximum value of the difference between the new policy, not new policy, the next evaluation and the current evaluation, and we wait for that change to be small enough that we could say it has converged. You can set a convergence criterion at 0.01 or 0.0001, or regardless, it will eventually get to that point when we call it good enough for convergence. It's close enough to the real values. It's not changing by very much on a per evaluation basis. So we only update the state values once. You can change this to twice or 3 times, but you update the state values a very small number of times at the policy evaluation step. And when you go into the policy iteration step, you're going to go through that same work. But as we just showed, a lot of that work is embedded already. So instead of trying to spend a ton of time figuring out the value of a random policy on a square that is right next to the goal, it doesn't take very much experience for that to converge. If you change the policy at that point, then places that are 2 squares away don't have to go through the random, like the exponential gain of needing to move left and then left to reach the goal. If you're 2 squares away from the goal that way, if the policy is random here, but is sure here, you don't need to luck into when you go here, it moves left. It will always move left. So you just need the 1 in 4 chance that this picks left, because 100% of the time now this is picking left. So in just 4 examples on average, you found the goal. Versus if this is also random, then you need to get left and then left, which is 4 times 4. And depending on how far away you are from the goal, this now creates, you need an exponential amount of data to lock into the solution. Whereas if this is guaranteed, you're taking out one of those exponents. You're reducing the exponent by one. And you can do that. And the way to see this asymptotically is to think that you're taking this problem and you're removing 3 of the options. And now this problem is way simpler for here to figure out how to get there. Just less work. It requires less data to see what this should be doing. That they should be picking left instead of up or right or down. Any questions on that? Yeah.
That doesn't necessarily mean that the first iteration wouldn't be random. Like the first iteration could be random, but the point is that you're changing it at a different time. Like you're adjusting it at a different time, even though it still will start in the first iteration.
Yeah. It would still start randomly, but with very little information, you go through the improvement steps. Some of the states are going to go from random behavior to guaranteed behavior. And that makes states that are next to it need less analysis in order to see that the correct choice is to move to that. And that just continues to propagate throughout your system and becomes much easier to learn. Very good questions. All one of them. Other questions? Okay. We will still do the same termination condition. So we're still going to terminate this when the changes that we make at the evaluation step are beneath the threshold that we call converged. However, this is going to happen much, much, much faster when we are evaluating, but cutting that off very quickly and then improving and then evaluating and improving. So it's something like you're going to take what was a 10,000 step process and you're going to break it down into a 2-step process and then a 2-step process and then a 2-step process and then a 2-step process and a 2-step process and a 2-step process and then it terminates. So there are going to be more iterations of this, but the work for each iteration is significantly less rather than doing a bunch of work on the one iteration that will find the optimal values overall. And that's embedded in the pseudocode here. Again, you would just implement this and you would have that idea. I don't like going through code line by line quite as much because it's just the math that explains the intuitive idea. I find the intuitive idea is what is the hardest to grasp in the first place. Yeah.
That requires more work on the person doing this, the user who's trying to evaluate this.
Not necessarily.
No.
What are you thinking? So what is the person responsible for?
Thinking policy.
That is going to, it's a greedy action selection. So you're going to pick all possible actions that we could pick. You're greedily going to select which one of these is best. If there is one of those, even from just 1 step or 2 steps, it's either going to be there is a best or it's going to be a tie in some capacity. If there is one that is the best, we're just going to pick that 100% of the time, greedily. And then if there are ties, so it's equally good to go here or here, left or up, then we can say, do this 50% of the time, this 50% of the time, this 100% of the time, this 100% of the time. In terms of the math that is underlying this, those would all be equivalent. The value of the state would be the same regardless of the weighting you give to this direction and this direction, as long as this direction's weight is 0 and this direction's weight is 0, the proportion of which you use and move between these look equivalent and are equivalent. Note that we can only do this because we have a perfect model of the underlying system. If you're playing a game like tic-tac-toe, you need to know your opponent's algorithm for picking which cells. If you don't know that, you can't play this. If you're playing chess against an opponent you don't know, even if you're playing chess against an opponent you do know, you can only have estimates for this and not real values. So you need to be able to see the entire system from the outside to be able to analyze it at this level and get this kind of result. Otherwise, we're making an assumption that might be wrong if our estimate for the values of these are wrong, and this is actually the best action to take, then this entire process falls apart. But when you know the entire underlying system, that can never happen. So you can use very specific algorithmic steps to make sure that you're optimizing the process. Yeah,
So if you do know the entire system, but the system does have the elements of randomness in it, then does that mean you don't know the whole system?
you do not know the whole system.
Okay.
And you'd have to use one of the ideas that I will disseminate once we're done with this section. Because there are most worlds that are out there, most systems are going to be that you don't understand them from the umbrella perspective, from the top down. You don't know how the entire system works. There are elements of randomness, elements of chance, elements of human behavior. So we can also use asynchronous dynamic programming. So instead of going over every single state, so in the grid world, there were 16 states, 14 of which we were updating. But instead of looking over all of that entire state space, we're going to use some other algorithm to systematically update. So you can look at things like how frequently are states visited. And you can update the more frequently visited states more frequently than the less frequently visited states. So you can take a process that if you understood grid world, you would know that the states that are closer to the goals are going to update and have information for us before those that are in the middle. So instead of looking at and sweeping the entire state space, you would sweep the state space near the goals and then update. And we would have the same information. Let me go back one more time to draw this out. You'd have the same information that you would otherwise. Does it matter that we updated this 0 to -1 to -2 here in the middle with respect to the rest of the state space? The answer is a bit yes, because we needed the -1 to be able to produce these -1.7s. But if this grid world were larger, if this were a 10 by 10 system, there's no reason after a couple of steps to sweep through and update the very middle squares. They're not going to be relevant to where the policy is going to update and be valuable. So you could selectively sweep the states that you know are going to be updated in the next pass, and then it saves you some of the work of updating that. Yeah. We can also intermix this and make it real time. So updating states according to the states that the agent is actively visiting or are near to where the agent is. If you have an infinite or massive state space, only go through and figure out the value of states that the agent can reach in a reasonable period of time. Think of this as kind of like if you're playing a real-time strategy game and you want to, so you don't need to be able to give a unit the ability to path from one side of the map to the other side of the map. You could use something that allowed you to figure out, and you keep things nearby to you to figure out what path should I take in order to get from here to there nearby. There's no reason to path all the way out and back, and that makes that system a lot easier because you're looking at a more localized version of that problem. And frequently in practice, we have very large state spaces. This entire process to understand the entire system all at once, that's a lot of pre-processing. It's the same thing like writing a really complicated program and then waiting 4 days for your program to compile before you can run it. Compile the parts of your program that are going to be run immediately, and while the remainder of your program is compiling, you may be able to use features of your program beforehand. Granted, modern compilers are so fast that it's not a problem, but that's kind of the idea. In order to converge, though, we must make sure that every state gets updated an infinite number of times until convergence. We can't just ignore one state. Once we think that it has converged, then when we iterate, there may be some updating for it to do still. This leads us to the overarching algorithm for all of this that we're going to call generalized policy iteration. This is how you should actually implement all of this. This describes most reinforcement learning methods, but it's just the exact process that we've seen of alternating between figuring out the value of a policy, improving that policy. So this is exactly what we've seen, except that we are slowly approaching the optimal policy and the optimal values of the states. We get closer and closer to that point, and eventually can conclude that we get there. We can also see it as a cycle. Value to improve to the policy, evaluate to the value, improve to the policy, etc. And we'll see this come back time and time again. The question is just, when we're not in a dynamic programming environment, what does it mean to come up with the values of states? We can't just look at the surrounding states and know what the value is based on our estimate of those values. We're going to need experience as we do that. We'll need to actually gather the data to be able to come to those conclusions. Yeah.
Is it possible that there could be more than one policy in a system that is optimal?
Yes. This gives you one of them. It's kind of like if you've ever seen a local search algorithm, a hill climbing type of algorithm, its purpose is to move up and up and up and up and up until it reaches a local maximum. A local maximum is no guarantee that there isn't a higher global maximum elsewhere. This isn't a problem here. It will find an optimal policy, but maybe there are multiple optimal policies. Instead of returning every possible optimal policy, it will return you one of them, whichever one it converges to, or whichever one is baked into the how ties are broken. If so, for instance, when we had that random and we chose this is good and this is good, this is bad and this is bad, an equivalent policy would pick this 100% of the time, this 100% of the time. These some arbitrary proportion of times doesn't really matter. Mathematically, they're the same, but in your code, it would, you could set how this tie is broken. If we look at north before we look at east, before we look at south, before we look at west, and break ties in that order, that would say that this happens 100% of the time. If we look at west and then south and then east and then north, this would happen 100% of the time. Another potential algorithm would say find every possibility that is the same and take 100% and divide that by the number of options. They would all look mathematically the same, but the bias would be inherent in the decisions that you make when you write the algorithm as to which policy gets returned. You just know that it would be an optimal one if the math works out to be such. Really good questions. Any others? How do we feel about generalized policy iteration? Silence. I'll take that to either be a good thing or a bad thing. You give me nothing, I give you nothing. A couple people gave me a thumbs up. If we're going to look at dynamic programming with regards to how efficient is this process, it's polynomial in the number of states and number of actions that the system is contained or contains. If we're directly searching the policy space, we're looking at every possible sequence of actions that we could take. That is exponential. We have the number of actions to the power of the number of states. Think of this like tic-tac-toe. If we're brute force looking at every possible game that could be played in tic-tac-toe, there are the actions, however many places that I could move, to the number of possible states that we, like, that's the largest possible state space that we could have. It is exponential, with the exponent being the state size, the number of states. So if we're looking at dynamic programming, we have reduced the exponential complexity down into something that is polynomial, something that is typically solvable for a reasonable number of states. So it's much more practical than thinking about this in terms of linear programming. If you have a large state space, you're going to use that concept of asynchronous dynamic programming. You're going to be looking at the states that are more likely to be updated sooner rather than later, or more relevant to where the agent is in its view of the world around it. Which states are similar to or closer to where the agent is, where the agent can likely go and visit, where you would like to have a more updated value for that state. And if you do have worst case guarantees on this, we find that in practice, we typically converge faster than that worst case guarantee. So the average case is very different from the worst case. All right, this is the end of talking about the concept of dynamic programming. Again, we use this when we have full knowledge of the system, so that when we look at math, it's based on data. Everything that is possible. If we need to learn elements of the underlying system, we need to gather data so that we can use that data to make these decisions. And that's where both Monte Carlo and temporal difference are going to lend their hand. So for Monte Carlo, we don't need complete knowledge of the environment. We don't need to know how many states there are in the system, for instance. All we need is experience. This is either experience from the agent actually interacting with the environment. It can also be simulated experience. So instead of launching the program and having the agent, if this is a terrain navigating robot, actually go navigate terrain, you could write a program that simulates the agent moving over terrain. So you can simulate experience and try to learn from that simulated experience before you transfer that simulated experience into the real environment. So as we do this, we're going to be getting more and more experience, but we need to figure out what these returns look like on average. So we'll end up averaging our sample returns. We still use that concept we just talked about, general policy iteration, where the prediction step is we're going to compute the value functions based on the experience that we have, and then we're going to improve our policies from the functions that we derive based on the experience that we collect. And when we talk about control, this is going to be how our policy updates, because we may end up needing multiple policies, and we'll talk about that in a second. So here is an example, and I remember there's an issue with this mathematically. We figure out what that was. So we play some game, and in this game, we receive a reward of 1 10 times, a reward of 0 2 times, and a reward of -1 0 times. So we're just going to figure out the average sample return. We have 10 times 1 plus 2 times 0 plus -1 times 0. The reward that we got and the sample, the number of times that we got it. This, I guess, should be 0 times -1. If we're going in the same order, this is the number of times the return, the number of times the return, the number of times the return. And this is the total number of samples that we collected. So we get an average return from this, which is still correct, of 10 over 12. We got a total of 10 reward. 10 times 1 plus 2 times 0 plus 0 times -1 is 10 for the numerator. 12 is the number of samples that we ran. So the average return that we got was just 0.587. 857. I'm not dyslexic, I swear. Questions on how that was calculated or what the average return for that was? Note that we know nothing about the system that this data was generated. How many states were there? What wins the game? What game are we playing? How does one win? How does one lose? With whatever policy we are using to gather this data, we have results, and we can start to analyze those results for any underlying how good is this policy? So as we get more and more experience, the value that we see here will converge to the actual value of being in that state according to the policy that's making the action selection. One thing to note as we do this, some states loop on themselves in certain systems. Imagine that you are playing chess and you move a rook, and that rook puts the king in check. And so the king moves out of the way of that check. Now that the king's out of the way of that check, you decide to move the rook back to where it went because it was in a better tactical position. Now that the rook is out of the way of the king moves right back to where it was. We have a cycle. We're back to the same state that we were in a couple of turns ago. The question is now, how do we come up with the value of being in that state? When do we update the value of being in that state? Do we update it just the first time we see it in a particular run? Or do we update it every single time we see that state in a particular run? So that is the first visit versus every visit problem in Monte Carlo. So first visit averages the return following the first visit to the state. And this is the usual typical way that this is done. And every visit looks at averaging the returns following every visit to that state. And that needs function approximation, some more advanced knowledge in order to figure out exactly how to do that. So what Monte Carlo is going to do is we have our initial state, and via some sequence of plays, this is a much larger state space than this, but this is the run that we experienced. That's kind of embedded down there as well, but you can imagine these are all different states until eventually we get some kind of outcome. I won the game at this point. This could be a game of tic-tac-toe, a game of chess. Doesn't matter, any learning situation. But we're going to take this outcome and we're going to back propagate this result to this state and this state and this state and this state based on how far away that state was to the outcome. So we're going to take the outcome, look at the process we used to get there. We're going to modify this state a lot, the value of this state a lot, because we immediately could win the game from there. This was 2 steps away, so we're going to make a little bit less update to this state, but it's going to be still significant because it was relatively close to the end result. And same thing, but we're going to have exponential decay on how much we update the value of each state from this run, because this state is probably in some kind of very large tree where there are a large number of actions that you could have taken. And the value of this state is going to depend on every possible path you could have taken from here all the way to the end of the game. How good is it to be in the initial state of chess? The fact that you won the game 80 turns later doesn't tell you much about how good it is on the first move of the game. It is relevant data, it's just not particularly relevant data. You would need much more information about how likely, you can imagine you don't think the game of chess is 50-50. How much data would you need to be able to answer that? A lot, because the state space is huge. Yeah.
But it would eventually even out because the first state would get updated way more at that time.
Right. Yeah. Yeah.
Just wondering about that example, don't you want? You don't want the value of your actions to change. If putting the king in check was the best move and going back is the best next move, don't you want it to loop and just continue doing that forever?
We'd end up in an infinite loop, which never evaluates the game. So if we had an agent playing an agent, that may end up being the situation. In which case we end up with a draw relatively quickly because rules of chess state if you make the same move 2 or 3 times, you end up in a draw.
I wasn't aware of that rule.
So if you end up in that infinite loop, you end up with a 50-50. So the player who has a chance, who has a better than 50% chance of winning, could probably be trying to avoid having that happen unless both players think it is exactly 50-50 and want to agree to that draw, then maybe that would be the case. But that also is a way to end the game not too far into the horizon. So that would become part of the anticipated value of being in that state. How frequently do you make the action that would immediately tie the game?
I mean, if you're trying to train a bot though, wouldn't it also try to accept that as like this is a neutral standing position? So especially if you're in the late game, wouldn't the bot want to try to cause a stalemate if they have that option and can force the other? bot
Maybe,
that's not-
depends on, I mean, if you have a knight and a rook and a queen left and they, on top of your king, and they just have a bishop.
Yeah,
You do not want that tie. You can force a victory. They want to force the tie
Mhm.
because they have a less than 50% chance of winning from there. So you should not agree to that if there's a way for you to win the game. If they can manipulate the game in a way that their bishop takes your queen and your knight, and you're left with a bishop versus rook endgame, sure, agree to that tie and do that. But there's a chance that you can win the game from there. So you should try to do so. Yeah.
In that example that you drew, all of those states are unique states, right? Sort of, you're trying to avoid the situation where one state gets updated multiple times. This is what we'll see.
Yeah, so you'd have to both update the state, since you saw it twice, once close to the end of the game, once farther from the end of the game. What does that mean about the value of that state? Do you update it multiple times because you visited it multiple times? Did you win because you visited it multiple times? Could you have won faster if you didn't do this middle garbage and had just taken this state to be that state and then won the game from there? Since it's the same state, you would have had that option. You don't want to learn that it's a good thing to waste time, basically, and that every visit could potentially learn to waste time. And delay victory as long as it's still guaranteed. Which is counter to what we might be trying to learn. So focus on first visit. It's an easier question to solve. So first visit, Monte Carlo takes his input, just a policy. Can be a random policy, doesn't matter what it is, we're just evaluating that policy. Then we initialize the value of each state to be a random number, doesn't matter what it is, for every state. For each state, the returns is just an empty list. This is just what was the value for the rest of the game every time we visited that state. Then for every episode, this is just gathering experience forever. Eventually this terminates. Whenever you can have it gain 10,000 games of experience, continue gaining experience until the clock hits noon tomorrow, then stop and dump all the data from that. So there's nothing that terminates this loop. It's just however much experience you want to get. Then you generate an episode. This just means that you're going to follow the policy. So you're going to start in the initial state, pick an action from that initial state based on the policy. Once you have that action, you get some reward and some new state. From that state, you're going to pick an action. And you're just going to continue to do that following the policy until eventually we reach termination. The game is won, the game is lost, the episode is over. You found the exit to the maze, whatever terminates the episode. We have the total return from that, and we're going to store that. So that episode is just as data, the states and actions that we visited and selected. Then we'll look at the return, looking back for every step in the episode, starting at the terminating time and moving backwards to the very beginning. We're going to set the return to be, we're going to discount the return. This is how we're going to prioritize states toward the end of the episode rather than states at the beginning of the episode. If you start at time t with a return of 1, then if your discount factor is 0.99, then a step away from victory or the end of the episode. You're going to multiply how much you update that state by that value. So as you get farther and farther away from the terminating state, you take the return that you got and you're exponentially decreasing it. As a way of weighting how far away from the termination condition you were, which means how related was that state to the eventual outcome. So unless this state appears elsewhere in the list, you're going to append this to the returns for that state. And then you can, for each state, calculate the average return that you got every time you visited that state over the course of every episode that you had. At the end of this process, you would have a large data structure for every state that just has a long list of every return that was calculated for every time that state was visited for the first time in every one of these episodes. That would give you an estimate based on the amount of time that you had for this experience, give you an estimate to the value of that state. Just based on the experience that you had the ability to collect. You get more experience, this is going to be more accurate. You get less experience, this is going to be less accurate. Law of large numbers will eventually kick in. That said, if you have a very complicated state space, this doesn't work so well, or you need more and more and more exponential experience to be able to make the same level of claim. How much experience do you need playing chess to know the value of an opening move? Just from whether you won the game or lost the game. Because of the sheer amount of states that can be visited all the way into victory or defeat. From there, you need billions of games of experience for that value to even remotely start to convert. All right, I think I have to leave it there. We're basically out of time already. So no class tomorrow. I'll have my typical meetings with each group on Friday. As I get a sense of how far are things coming, how's your game coming along? And I'll try to give you some feedback to help push you toward a successful game project. So I'll see you Friday for that.
Yes. Later.